Hello, this is a video on an OCR A-level chemistry. It's an old paper, F324 from June 2011, and the purpose is to try and show you how to approach NMR questions and other analysis and chromatography. So, question 5 in this paper starts off by letting you know that forest fires release a large number of organic compounds, and they then state that you're going to be using GCMS to identify the compounds. Now there's 2 marks here, so it's for identifying what the 2 different parts are. GC for gas chromatography. Hopefully you'll know chromatography is all about separating the compounds. You could also have put components. So use your gas chromatography to separate the compounds, and then once that's done, what the mass spec is going to do is it's going to be used to identify the compounds, but that's not going to be specific enough. You have to put how, and it's about comparison with a database. So that's the key thing. You could put reference, refer to, that concept. Now if you really want to go to town on it, it's about matching the fragmentation patterns that you get in your mass spec. Okay, part B is continuing on with this identification theme analysis. They give you compound F and they tell you a percentage. Now most of you, your first thought is going to be, oh great, we're just going to be taking the percentage, dividing it by the relative atomic mass, but you only have that one for oxygen and there'll be 2 other unknowns, so that's not what we're going to do. So we've got to again just underline the key information. We know that it's 54.2% oxygen, and we know the molar mass is 118, but then we're actually given what the formula is going to be, and we're asked to prove this. So at this point, we know we're working about masses. What I'm going to look to do is figure out what mass each of the various elements would contribute. 4 carbons, 4 times 12 is 48, 6 hydrogens is 6, and there's 4 oxygens, 4 times 16 is 64. Now the only information I've got otherwise is it's 54.2% of the compound is oxygen. Given it's 118 grams per mole, let's work out what 54.2% of 118 is, and that would be 63.96, which we can essentially say is 64. So we get that these 2 match up. Now we'll work out what's remaining. So there was 64 grams out of every 118 came from oxygen. So if we take that away from the 118, we find that there is 54 left. And then if you just show that that's 6 grams from the hydrogen and 48 from the carbon, putting all that together. Okay, the next one is an infrared. And the biggest mistake people make here is they don't RTFQ, read that full question. Name the functional group. So looking on here, we've got this really broad peak around about 3000 to 3300. So we know that's coming from an OH. We've got this sharp peak here, and that's coming from the C double bond O. But if we put these 2 together, we know that we've got a carboxyl functional group. So again, name it. So many people would just put in the OH or the COOH. Alright, here we go, the main event. So it is an NMR question, it's a proton NMR, and key thing, it's the same compound that we already know. Bring that information over. We know that we've got a carbonyl as part of it. So the very first thing I'm looking for in a proton NMR is how many peaks we've got, because the number of peaks equals the number of proton environments. Now there's this little peak down here, but again, reading the full question, they tell you that they're using this deuterated DMSO, dimethyl sulfoxide, and there's some TMS added. Hopefully you all remember that that is this thing down at 0. We will talk about that in part 3 of this question. So the thing that you want to do is lay out what each peak is and then work out what environment, and you will use your data sheet, you will use the chemical shift to work out what that's telling you. For some questions you'll also have the integrations, the relative integrations. We don't have that here, we just have the splitting. Now there are 4 marks, and what it wants us to do is use these chemical shifts and these splitting patterns to get to the structural formula. So 11.0 ppm, we know if we use the data sheet that that is the carboxyl hydrogen, and we already knew that group had to be in there. I'm going to cut across with the splitting here. There's a broad singlet, and the key thing, there's nothing adjacent to this because it's the coup, so we can put that there. There's no link to it. Next thing, 3.4 ppm, but it tells us in the question that we would expect it to be at 2.4. And if you look at the 3 possible things this could be, it could be with a nitrogen. Well, we know there's no nitrogen because the formula is C4H6O4. It could also be aromatic. It can't be aromatic. We don't have enough carbons and to be able to get the aromatic ring. So what this must be is a carbon, the hydrogen on a carbon which is bonded to the carbonyl. So it's not the hydrogen directly to a carbonyl, so it's not an aldehyde, it's a hydrogen on a carbon which is next to the carbonyl. And then this one down at 0.8 ppm is just RCH. And what I'm doing is I'm underlining the hydrogen that's responsible each time. So this right now would get me 1 mark because I've used the chemical shifts. The next thing we've got to do is talk about the splitting patterns, and the final part is the structural formula. To do anything with splitting patterns, we need to use the N+1 rule. N is the number of hydrogen on an adjacent carbon. So I'll try and talk through that slowly just now. The splitting pattern comes from N+1. Up here there are 4 peaks within this peak, as it were, giving us the quartet. So N+1 equals 4, so we know that N equals 3. That means that this hydrogen here is adjacent to 3 equivalent hydrogens. So it's adjacent to a CH3. The CH3 didn't cause this peak, they've caused some other peak. Next one down. This hydrogen or hydrogens, again, we don't have the relative integration so we can't tell for sure, but this peak is split into a doublet. So N+1 equals 2, which means that N equals 1, which means that they are adjacent to a carbon with just 1 hydrogen. So it's a carbon that must have 3 things that are not hydrogen. If you were able to do these 2 parts here, and just to state, again, working it slowly down, count up, there's a quartet, which means N+1 equals 4, so N equals 3, so therefore it's adjacent to the 3 equivalent hydrogens, which must be a CH3. That was 1 mark. This one is a doublet, N+1 is therefore 2, so N was 1, so it's adjacent to a CH. So this means that this hydrogen here bonds to a carbon, which is then bonding to that carbon with 1 hydrogen on it. Now at this point, what I always try and do is have my goal. I've got to somehow account for 4 carbons, 6 hydrogens and 4 oxygens. I know from here that there was a coup, a carboxyl. So I'm going to subtract that, and I'm left with C3H5O2. So I know somewhere in this molecule there's a coup, and the rest of it accounts for C3H5. Now we know that there has to be a CH3 somewhere, and it's got to be next to this one because the 2 things are linking to each other, so you've got the carbon and the hydrogen in the middle of the molecule like this, because they're the only things that could be doing that. So this is 2 carbons and 4 hydrogens, so if we take away C2H4, what we're left with is CO2H. We know that there was one carboxyl group, and it turns out there must be another carboxyl group. So it was a really quite sneaky thing where they put in the fact that there were 2. You might then just want to draw all of this out. You can see there's a carboxyl group at either end, and you've got the CH here, which splits this methyl group into the doublet, and the CH3, which splits this 1 proton into the quartet. And were they to have given us these relative integrations, that one would be a 1 and that one would be a 3, because the 3 tells you about what it actually belongs to, and the doublet tells you what it's next to. Okay, there's just a couple of last questions here, continuing with the NMR theme. They want you to explain why deuterated dimethyl sulfoxide was used as the solvent. So the solvent is because all of this has to be done in solution, and you want a solvent that's not going to obscure what you're seeing. If you just used a standard solvent that had regular protons on there, you wouldn't be able to see the NMR spectrum from your sample. It would be like trying to look for the stars in the middle of a really bright day. The light from the sun would basically obscure them. The thing you've got to remember is deuterium, is this is 2H, which is an even number of nucleons. That's 2 is even. And the key thing is that you will get no peak visible. So you get no peak shown because it's even numbers. Okay, next thing down, TMS stands for tetra methyl silane, which is a silicon with 4 CH3s, and the whole point of using this is it is the standard or the reference. It is something which is going to give you this chemical shift of 0 because they are not de-shielded, because it's about as non-polar as we can get. Right, the very last part of it, D2O, and why we would use D2O. You have a thing which is called proton exchange. And what happens is that when you've got polar bonds between, say, an oxygen or a nitrogen and hydrogen, so for these bonds you've got a delta positive hydrogen, just as you would do here. And what happens is that they're mildly acidic, so they do dissociate, and they end up swapping. So the hydrogens that were on here from, say, an alcohol or a carboxylic acid end up being replaced by the deuterium from the D2O. So simply the D replaces the H in the NH or in the OH bonds. And why this is significant is because if we were to run our compound F, the peak at 11.0 ppm, which we've already stated came from the carboxyl group, that would disappear. Thank you very much.